Hello, this is Kaiwen Zhou, and I'm here to present our work on a new momentum trick for stochastic optimization. This is joint work with Yanghua, Qinghua, and James Cheng. To begin with, let's review some classic momentum tricks. The most well-known momentum techniques are definitely Nesterov's momentum and heavy ball momentum. They are called the momentum scheme because the underlying part, which is understood to be the momentum that boosts the convergence rate over standard gradient descent. So if we set beta equals to 0 here, both schemes reduce to gradient descent. There are already a lot of study on what's the difference between these two schemes, so we are not going details here. A distinctive feature of Nesterov's momentum is that it achieves the optimal 1 over k square rate for general convex objectives. Well, and thus, as our title suggests, our new momentum trick will be built upon this famous Nesterov's momentum. To provide some insight on how Nesterov's momentum work, here we show some visualization on how the Nesterov scheme is differentiated from the gradient descent. So here we have a sequence of gradient descent denoted as x here. The first step Nesterov's momentum does is to store the result of gradient descent into another sequence y, and then it takes the offset in the sequence y, which is from the previous iterate of y, and uses it as the momentum to inject into the sequence of x. So we can understand that the momentum is provided by the previous iterate of gradient descent. The important question is that what if we only have stochastic gradient? A direct thought is we can simply replace the deterministic gradient in the previous scheme and use stochastic gradient instead, which results in the famous scheme, well, a widely used scheme in deep learning community, which is implemented in PyTorch and TensorFlow and used extensively in tasks such as image classification. So, however, there's an issue here. Following the previous insight, now in the stochastic case, the momentum is provided by a previous iterate of stochastic gradient descent. However, this means that this momentum now potentially have a very large variance, which may lead to a false momentum that perturbs the training process. So we aim to solve this problem. Our high-level idea is that instead of looking at merely one previous iterate of SGD, we look at several past iterates of SGD. We call the new momentum trick amortized momentum. Here we show a sequence of past iterates of SGD, and we introduce a new parameter m here, and we divide the sequence of SGD into several epochs, each contains m iterates. So the first step we do is to aggregate information in each epoch into another variable tilde x, and then basically we use average here, so we can understand it's like two consecutive tail average of SGD, and then we take the offset between these two tail average and use it as the momentum injected at the end of the epoch. As you can see here, our new momentum is theoretical, but it is expected to be much larger than the Nesterov's momentum. So informally, we can understand it we injected m times larger momentum in every m iteration. But the difference here, that's why we call it robust, is the momentum is provided by a tail average, which is expected to be much more statistically stable than merely a single step, and will affect much less by the variance of the gradient. We proved that in a convex case, if m is small, our schemes achieve optimal rate. So just like the natural momentum, so we does not lose the advantage of natural method. And if the stochastic noise is large, that it contains large variance, our new schemes are actually faster than the natural method. And there are some interesting connections between our proposed scheme and those existing schemes, such as mirror descent and CUHK and natural method. Motivated by the success of using momentum in deep learning, we extend our schemes to the deep learning setting. Here we show a typical experimental result, and AMSGD is the proposed scheme. There's an output option here, but it will be clear in the paper. So as you can see here, our momentum trick provides a better robustness and actually a better overall performance. It achieves similar final accuracy as the MSGD, but is much smoother. And actually, if we implemented it correctly, it has lower iteration cost. Yeah. And that's all of our presentation. Thanks for your attention.